I'm Anil Kumar. In this particular video, I'm going to discuss in details how to do curve sketching for rational functions. The example is to sketch graph of f of x equals to 6x squared minus 2 divided by x cubed. Now this is a rational function. So in rational function, we will first look into asymptotes. So as you can see, in this particular case, we have two asymptotes. One is horizontal asymptote. Since we know that the degree of numerator is 1 lower than that of denominator, x-axis is our asymptote, whose equation is y equals to 0, right? So horizontal asymptote is y equals to 0, which basically is x-axis. Now in this case, we also have a vertical asymptote, and the vertical asymptote is when x is equal to 0, which is y-axis, correct? So both axes will act as an asymptote. Now let's also look into the intercepts. As far as intercepts are concerned, we will not have any y-intercept since we have a vertical asymptote, right? We do have a horizontal asymptote. However, you can see it has x-intercepts, right? So to find x-intercept, we can equate numerator to 0, which is 6x squared minus 2 equals to 0, and that gives you the value of x as equals to, if you take it to this side, it is 2 over 6. We can say x squared is 2 over 6, right? Bringing 2 and then dividing by 6, or this implies that x is equals to plus minus square root of 1 over 3, right? So that becomes the x-intercept for the given function. And now we'll check the symmetry, right? We'll check symmetry now. To find symmetry of the graph, let's figure out what is f of minus x equal to. If I substitute minus x, I get 6 minus x whole square minus 2 over minus x whole cube. And this is equal to 6x squared minus 2 over minus x cube, or it is minus of f of x. Now since f of minus x is equals to minus of f of x, we have odd symmetry, right? So these are primary characteristics which we can find even without finding derivatives. Now let's get back to derivatives. Let's find the first derivative for the function. Now first derivative, we can apply product rule or quotient rule. So let me apply the quotient rule. So we'll have denominator as x to the power of 6, that is square of cube. In the numerator, derivative of 6x squared minus 2 is 12x times x cubed minus derivative of x cubed is 3x squared times 6x squared minus 2, right? Now this can be simplified. We have 12 x to the power of 4. Open this up, we get minus 18 x to the power of 4, and 3 times 2 is 6. We get plus 6x squared over x to the power of 6. Now we could write this as 12 minus 18 is minus 6. So we can write this as minus 6 x to the power of 4 plus 6x squared over x to the power of 6. Taking minus 6x squared as common, we get x squared minus 1 divided by x to the power of 6. We're cancelling these. We get minus 6 x squared minus 1 over x to the power of 4, right? So at this stage, we cancel this with 4. Okay. So that is the first derivative. Now we can analyze this first derivative. The critical numbers to look into are when this derivative is either 0 or undefined, correct? So the critical numbers are at, let me write down. So the critical numbers are when f dash is equals to 0, that gives you x equals to plus minus 1, and undefined when x is equals to 0, right? So we can analyze on either side of these numbers. So taking them into account, we have 0 here, minus 1 plus 1. The function is minus 6 x squared minus 1. Now remember, denominator is always positive, so this is always positive. Is it okay? So we'll test the numerator now for the values in these intervals. So if I take a value which is, let's say, minus 2, we can take minus half, we can take plus half, and 2. So if I take a value of x which is greater than 1, or I mean absolute value 1, let's say minus 2, then this part will be positive, but this will be negative, right? So we get negative here in that interval. So I could show this as, so we are analyzing the first derivative. So when I substitute minus 2 here, I get negative. If I substitute half, I get positive, because negative will make it positive. Same is the case with positive half, and for 2 it is going to be negative. So clearly we do have a minimum and a maximum. So what we get here is minimum at x equals to minus 1, and maximum at x equals to plus 1. So that gives you maximum, correct? This is minimum. Now if I substitute 1 here, what is the value of y? So what is f of minus 1 equal to? Minus 1 is going to give me 6 minus 2, which is 4, divided by 1, which is minus 4, right? So we get minus 4 here. And on substituting 1, we get f of 1 as equal to 6 minus 2 is 4, divided by 1 is 4. So we do get two critical points, which is maximum and minimum. Let me write it in red. These are minus 1, minus 4, and plus 1, plus 4. Great. Now let's move on to the next page. We'll find the second derivative and apply all this learnings to sketch the curve. So let me copy this function first, which is minus 6 times x squared minus 1 divided by x to the power of 4. So here is what we have, the function itself, and its derivative is minus 6 x squared minus 1 over x to the power of 4. Correct. We also found that we have maximum at 1, and the value was plus 4, and we have minimum at minus 1, minus 4. Perfect. Now from this derivative, let's find what is the second derivative. So we'll again apply the quotient rule. So we get x to the power of 8. Derivative of this portion is minus 12x, and here we get x to the power of 4 minus derivative of x cubed, x to the power of 4 is 4, x cubed, times all this. Minus and minus makes it plus. We have times 6 times x squared minus 1, right? Let's open this up. We have minus 12 x to the power of 5 plus 6 times 4, 24, x to the power of 5, and 24 x cubed divided by x to the power of 8. So that gives us 12x to the power of 5 minus 24 x cubed over x to the power of 8. And let me do it on this side. Here we'll sketch the graph. Okay, so we could take 12x to the power of 3 common. We have x squared minus 2 divided by x to the power of 8, and that gives us 3 cancels. We get 12 times x squared minus 2 divided by x to the power of 5. Now clearly we do have two zeros, so if I want to find the critical numbers here, then they are at x equals to plus minus 2, right? So let us analyze this graph at x equals to plus minus 2 for concavity. So what we get here is that the second derivative is equals to 0 for x equals to plus minus square root of 2. And there is a critical number at x equals to 0 also, which is a denominator, which is a vertical asymptote. And we have another critical number when denominator is 0 at x equals to 0. So let us analyze this function for second derivative. So we have 0 and plus minus square root 2. Now clearly denominator is, if I put a negative value, it will be negative. Now if I have a value which is on the left side of square root 2, then numerator is going to be positive, right? But the denominator is negative. So in this portion we'll get negative. But if I have a value between square root 2 and 0, then the numerator is going to be negative, denominator is also going to be negative, we'll get positive. And since this function is odd, we could actually conclude also what is going to happen here. If it is positive, denominator is always positive, numerator is going to be negative for between 0 to square root 2 and positive when it's greater than 2. So that gives us the concavity. Negative means concave down, and here we have concave up, concave down, concave up. So we are looking for 2 point of inflections, right? So we have a point of inflection at square root 2 plus and minus. Here actually the concavity is changing, however there is a vertical asymptote, right? So since there's a vertical asymptote, we can say there is no point of inflection here, but we do have point of inflection at plus minus square root 2, right? So these are the 2 points where we do have point of inflection, right? Now with that information, we should be in a position to sketch the graph. So let me make our x and y coordinates. And also put down all the values which we have. So what we learned here is that since the degree of denominator is higher, we have a horizontal asymptote, and that becomes the horizontal asymptote. Perfect. Vertical asymptote, x equals to 0. We have vertical asymptote. Now, we found that the maximum is at 1, 4 and minimum is at minus 1, 4. So let us say, let's say this is plus 1 and this is minus 1 for us. Okay. So let us say this is minus 1 and that is plus 1. Here we are looking at concavity at plus minus square root 2, which is 1.414, right? So concavity somewhere here, right? 1, so this is minus 2. Here it be like minus 2. So 1.414 will be somewhere on this side. that's a negative value, and 1.414 somewhere on this side. Okay, we are looking for the point of inflection, right? So we have maximum, minimum and maximum, and now let's recall what is x-intercept. Now the x-intercept was when the numerator is 0, which is square root of 1 by 3, which is kind of 0.5. So we have somewhere here the x-intercepts, which we get by equating numerator to 0. Perfect. Now we also know that this graph is odd. That means it is same reflected on origin. Correct? Now, joining all these things, all what we know, and we have horizontal and vertical asymptotes. If we are very close to 0, right, somewhere very close to 0, in that case, if I approach from the negative side, then both are going to be negative, so we are approaching positive infinity. If I approach from the right side, this is positive, that is negative, so we are approaching negative infinity. So I hope you understand this part, behavior near the asymptote as we approach 0, the vertical asymptote from either side. If I substitute large positive value, then all this is going to be positive, and therefore we are going to approach horizontal asymptote from positive 0. If I substitute negative large value, in that case the answer will be negative, slightly less than 0, approaching 0 from the negative side. So that is what we get. Now joining all this, so we have somewhere along this side our minimum, right? So, and concavity along this path. So we could join this kind of like this, turn. So that turning will happen at -4, right? And so it's concave up. Do you see that? It's concave up. This portion we are sketching now. So it's concave up. However, the concavity changes as we approach square root 2 minus. So it becomes concave down and then approaches 0. Do you see that graph? That is how you could actually sketch this particular function. Similarly, on this side also, we have an x-intercept here, and somewhere here at 1, 4. So somewhere here at 4, we have a turning point, which will be the local maximum, right? So we can go like this, turn, come down. This is concave down. Do you see that? All this should have been smoother curve. Okay. And after that, concavity changes. So that's how the graph will look like, where this turning happens to be at 4 and 1. And the minimum local will be at -4, 1. That intercept for us is at 1 over, this is this part, x-intercept, which is when the numerator is 0, this part, right? When this numerator is 0, 1 over 3 square root. So this is square root of 1 over 3. Here this is going to be square root of -1 over 3. Perfect. And that's the maximum, correct? Point of inflection will be at minus and plus square root 2. So I hope with this you can see clearly how we can analyze and then sketch curve for the given rational function. I'd like you to go through this in details and understand how to do curve sketching for a rational function. Hope you like and appreciate it. Feel free to write your comments, and if you subscribe, that'll be great. Thank you and all the best.